We now want to look at a few different models on how to measure the optimality or the quality of a binary search tree. The first one is the one that you know. If we have a fixed binary search tree, what is the worst sequence of queries that we can have? In the example we had before, this is one of them. We have to go all the way down to a leaf at the lowest level, then up and down again, and so on. And as we know, the lowest leaf always has depth log n, so we cannot do better than omega of log n per query. And we say that a tree is balanced if we can reach this bound. So if you only have a single query, then that query should take log n. But if we have a sequence of queries, then the running time in total should be order of m log n if we have m queries, plus n log n. So if we have at least n queries, then that means that the amortized cost of each query is only order of log n. So there can be some queries that take a long time, but they have to be offset by others that are very short, so that on average we only take logarithmic time to do a query in the sequence. In the second model, we have a known probability distribution of the keys. So we have a tree, and for each key we know what is the probability that this key will be queried. So we don't know the exact sequence that will be queried, but we know how likely it is that number 5 will be queried here. How would you build a tree if you only know the probabilities and want to make sure that the queries will be short? Well, the first idea is, of course, we take the one with the largest probability and put it into the root, and then next those with the second largest probability, and so on. Of course, this does not always work, depending on how everything is distributed. For example, if the probabilities go down from left to right, then that would give us a very unbalanced tree. But optimally, we would want to have nodes with higher probability to be higher in the tree. In particular, what we would like to have is, if we look at level 2, that all the nodes here have probability at most 1 over 2. So that the probability to go here is not too large. And if we look at level L, then we want that each of these keys has probability at most 1 over 2 to the L minus 1. So that we have to go L levels, the probability is very low. We can achieve this for this sample probability distribution by this tree. This has exactly this property. So optimally, we would want a key that has probability p to be set into which level? Well, if it has probability p, then we want it to be, we have to reverse this, level log 1 over p or higher. And if we can achieve that for every vertex, then we get the following bound. The expected query cost is at least omega of 1 plus h per query, where h is the following formula. Every node contributes its probability times the level it is in. So we have the sum over all of them, probability times log 1 over probability. It's not clear that we can always do that, but in the optimum we definitely get this, because the optimum would look like this. So we definitely cannot do any better than that. And we say that a binary search tree has the entropy property if it reaches this bound. Let's have a look at two small examples what this means. For example, let's say that all of them have the same probability 1 over n to be queried. Then the sum of these is 1 over n times log n. And if we sum this up, this gives us exactly log n per query, or 1 plus log n per query. Or one of them has the probability 1, so we will only always query the same key, the others have a 0. Now we see a small problem, because now we have 1 over 0 here, so let's rephrase this a little bit. We know that log 1 over something is just minus log the something, so we can rephrase this like this. And now if we sum this up, all of those are a 0 for all the pi's except p1, so this is just minus log 1, which is a 0. So the expected query cost is exactly 1 for each query because we put it at the root. In the third model, we look at the spatial locality. What we want is, if we want to query a key, then the keys with nearby values are more likely to be queried. So suppose that we queried some key xi, and next we want to query the key xj next. So we have this example and assume we queried number 11, and next we want to query number 13. The 13 is very close to the 1, so it is more likely to be queried, so we want it to be fast. And to define this a bit more clearly, we define the delta function, which is the difference of the ranks. So the 11 is the 7th smallest number, so it has rank 7. 13 is the 9th smallest number, so it has rank 9. So the rank difference between them is a 2. And then we want a running time that is asymptotic to this number. And this is what we call the dynamic finger property. We want that the amortized cost of all queries are in order logarithm of the rank difference between the last two queries. And in this tree here, it's a problem because we have to go all the way up and then all the way down again, so the difference is 2, but we take log n time, so this does not have the dynamic finger property. But we can easily fix this by also linking the nodes of the same level. This is a so-called level-linked balanced tree. For example, a level-linked red-black tree. And if we can use these links, then we can easily go from 11 to 13, and then we can do it in constant time. And a level-linked red-black tree has defined dynamic finger property as defined here. Model number 4 is the temporal locality. And that says if a key is queried, then it's likely that we will query it again soon. For example, if you look for something on Google, there are many pages, but if you've already looked for something, then the probability that you will look for it again is much higher than something that you have never looked at. If we have a static tree, then this will be very tough. So we somehow have to allow the tree to change. For example, we can move elements around. And the idea I want to present you here is that we use a sequence of trees. So each of them is a balanced tree. We have one tree with just 2 levels. Then we have one tree with 4 levels that is linked. Then we have one with 8 levels, one with 16 levels, and so on. So we always double the number of levels that we have. And now if we want to query something, we first look for it in the first tree. If it's not there, we look in the second one. If it's not there, then the third one, and so on. And also, whenever we find a key, we want to move it to the first tree and kick out the oldest. So the oldest now moves to the second tree, the oldest from the second tree to the third, and then we have the same number of elements in each tree again. And if we do this, then we get the working set property. The working set property tells us that the amortized cost of a query for key x is order of log t, and t is the number of keys that have been queried more recently. And it's not so hard to prove for this sequence of trees that we get the working set property. So when something has been queried recently, then it's in one of the first trees, and then we don't have to look at too many trees, they don't have too much of size, so we can quickly access it again. And the fifth one, which is maybe the most important one, is the static optimality. Let's say we have a sequence of queries. There has to be some optimal static tree. So out of all static trees that you can build, there is one tree that has the shortest total query time for the sequence. So for our example in the beginning, we have the sequence 2, 5, 2, 5, 2, 5. Then the optimal tree would look something like this. We have the 2 and the 5 at the very top, and we only take constant time for each query, exactly 1 time here, so the optimum is S, or order of S. Now we say that a binary search tree is statically optimal if the queries only take amortized asymptotically as much time as this static tree. This search tree does not have to be static, so we're still allowed to move things around. And that's the key part that we will require later, that we can build one dynamic tree that is for any sequence as good as the optimal static one. So we have 5 properties. We have balanced, we take amortized logarithmic time per query. We have the entropy, we have expected time that depends on the probabilities. We have the dynamic finger. If they are close, then we only take little time. We have working set. If something has been queried recently, then we want to query it again fast. And we have static optimality. All those queries do not take asymptotically more time than the optimal static tree. And the big question is, of course, is there some binary search tree that has all these properties? So we don't need a different one for whatever we want to do. And the answer is yes, there is. And that is the Splay tree. And that one I will show you in the next part.